Hello and welcome to Electro Nerds Academy. In this video, we're exploring one of the most widely used communication protocols in microcontrollers, I2C, also known as Inter-Integrated Circuit, I2C, I2C, or simply the two-wire interface. I2C protocol was developed by Philips in the 1980s to let a microcontroller communicate with multiple peripherals, such as sensors, displays, and memory devices, using only two wires. SCL, serial clock line, which carries the clock signal, and SDA, serial data line, which carries the data signal. Both lines are bidirectional and use an open drain configuration. Let's see what it means. Imagine two devices connected through the SDA and SCL lines. Each device has an internal switching element, usually a transistor or MOSFET. Both lines have pull-up resistors, commonly 4.7 kiloohms or 10 kiloohms, connected to VCC. Because the drains of these transistors are not directly tied to the supply voltage and are left open, the configuration is called open drain. When the bus is idle, both SDA and SCL remain high due to the pull-up resistors. If any device wants to send a low, it simply turns on its transistor and pulls the line to ground. To send a high, the device just releases the line and the pull-up resistor pulls it back up. This means in open drain configuration, no device ever actively drives the line high. They can only pull it low, and the pull-up resistors keep the lines high when idle. I2C protocol uses a master-slave architecture, where the master, usually a microcontroller such as an Arduino, initiates and controls all communication. The slave devices, such as sensors, displays, and memory modules, respond to the master's requests. Each slave on the bus has a unique address, usually written in hexadecimal format, typically 7 bits long, and sometimes 10 bits, which allows multiple devices to share the same two-wire bus without conflicts. Since I2C protocol typically uses 7-bit addressing, its address ranges from the lowest 7-bit value, which is 0 in decimal, to the highest 7-bit value, which is 127 in decimal. That technically gives us 128 possible addresses, which means we could, in theory, connect up to 128 devices to the same I2C bus. But in the real world, 16 of those addresses are reserved, so we're left with around 112 usable addresses. Even then, we normally can't connect that many devices with our Arduino. Realistically, we can reliably connect only about 10 to 20 devices. That's because every device we add behaves like a small capacitor on the bus. And as the number of devices increases, the total capacitance increases, which causes the signals on the SDA and SCL lines take longer to rise and fall, which can cause communication errors, especially at higher speeds. Now that we've seen how I2C addressing works, let's move on to how communication actually happens on the bus. Communication always begins when the master generates a start condition, which occurs when SDA goes low while SCL is high. This alerts all devices on the bus that a transmission is about to begin. The master then sends the 7-bit address of the target slave. For example, if the master wants to communicate with the second slave device, it sends that device's unique address on the SDA line. After the address, the master sends a read-write bit, 1 for read and 0 for write, to indicate the direction of data flow. After every byte, the transmitter releases the SDA line for 1 clock pulse. The receiver then responds with either an acknowledged or not acknowledged bit. Pulling SDA low indicates an acknowledged bit, meaning the byte was received correctly. Leaving SDA high indicates a not acknowledged bit, meaning the byte was not received. This handshake ensures reliable communication. Once the address is acknowledged, data transfer begins. If the master is writing data to the slave, it sends data bytes one by one, and the slave acknowledges each byte. If the master is reading data from the slave sends the data bytes, and the master acknowledges each one. After the final byte, the master sends a not acknowledged bit to signal the end of the transfer. Finally, a stop condition is generated. This occurs when SDA transitions from low to high while SCL is high, indicating that communication has ended and the bus is free for other operations. Thankfully, there is a built-in Arduino library called the Wire Library that handles all the complexities of I2C communication. This library provides a number of useful functions as shown. Let's explore each of them in detail, starting with the begin function. This function initializes I2C communication and configures the Arduino to operate either as a master or a slave. If we want the Arduino to act as a master, we call this function without any parameters. If we want it to act as a slave, we call this function with an address as a parameter, after which the Arduino operates as a slave device with the specified address. Next, we have the request from function. This function is used by the master to request data from a specific slave and store the received bytes in the wire library's receive buffer. It takes two main parameters. The first is the 7-bit address of the slave device, and the second is the number of bytes to request. An optional third parameter called the stop bit can also be provided. When set to true, the Arduino sends a stop condition after the request, releasing the bus. When set to false, it repeatedly sends a restart condition after the request, keeping the connection active. This function returns an unsigned 8-bit integer that indicates how many bytes were actually received. Next, we have the available function. This function tells how many bytes are available to read in the receive buffer. It takes no parameters and returns an integer value indicating the number of bytes ready to be read. After that comes the read function, which actually retrieves the received data. This function takes no parameters and returns the first available byte from the receive buffer each time it is called. If no data is available to be read, it returns -1. After the read function, we have the write function, which is used to send data over the I2C bus. This function can transmit a single byte, such as a character, or multiple bytes, such as a string. It can also send an array of bytes, in which case two parameters are used, the array name and the number of bytes to be transmitted. The behavior of the write function differs depending on whether the Arduino is configured as a master or a slave. In slave mode, when the master requests data from the slave using the request from function, the slave uses the write function to send the requested data back to the master. In master mode, the write function is used between the begin and end transmission functions. In this mode, the write function does not immediately send data to the slave. Instead, it places the bytes into a transmit buffer. The actual transmission occurs only when the end transmission function is called. Now, let's look at the begin and end transmission functions, starting with the begin transmission function. This function is used by the master when it wants to send data to a slave device. It takes a single parameter, which is the address of the slave device the master wants to communicate with. Next is the end transmission function. This function ends a transmission with a slave device that was begun by begin transmission and transmits the bytes that were queued by the write function. This function returns an unsigned integer status code that indicates whether the transmission was successful or not. A return value of 0 means the data was sent successfully. A value of 1 indicates that the data was too long to fit in the transmit buffer. A value of 2 means a not acknowledged bit was received after the data transmission. A value of 3 indicates that a not acknowledged bit was received in response to the address transmission. A value of 4 means that other errors were encountered during transmission. Next, we have the onReceive function. This function is used by the slave device to register a custom function that is automatically called whenever the slave receives data from the master. It takes a single parameter, which is the name of the user-defined function. For example, if we pass a function named receive as the parameter, that receive function will be executed automatically whenever data arrives from the master. An important point to highlight here is that when this receive callback function is called, it is automatically provided with one parameter, the number of bytes received from the master. Therefore, when defining this function, we must include an integer parameter to capture this value, regardless of whether we choose to use it inside the function or not. Finally, we have the onRequest function. This function is also used by the slave device, but it registers a custom function that is called when the master requests data from the slave. It takes a single parameter, which is the name of the user-defined function. For example, if we pass a function named request as the parameter, that request function will be executed automatically whenever the master requests data from the slave using the request from function. In an Arduino Uno, the I2C pins are analog pins A4 and A5. A4 is the SDA pin and A5 is the SCL pin. However, different Arduino models have different SDA and SCL pins used for I2C communication. Now let's hook up two Arduino boards and make them talk to each other via I2C protocol. One Arduino will act as the master and the other as the slave. We're using two Arduino Unos, but you can use any model. Just refer to the chart we discussed earlier for the correct pins. Here's how the connections look. We will connect the GND pins of both the Arduinos together. We connect SDA to SDA and SCL to SCL. Next, we will add two 10 kilo ohms resistors, one from SDA to 5 volts and one from SCL to 5 volts. Now let's look at the code. We will have two sketches in total, one for the master and one for the slave. So let's see the master sketch first. At the top of the code, we have included the wire library and defined the slave address, which in this case is 9. This address is chosen by us and can be any value between 8 and 127, as long as it doesn't conflict with the address of another device on the I2C bus. However, real I2C devices like sensors or displays usually have fixed addresses, which you can find in their datasheets. Next, we define the number of bytes we expect to receive from the slave, which is 5 bytes. In the setup function, we initialize I2C communication using wire.begin function. Since no address is provided, the Arduino acts as an I2C master. We also initialize serial communication with 9600 baud rate. Inside the loop function, we first add a short 50 millisecond delay. Then, we print a message on the serial monitor indicating that we are about to send data to the slave. We then start the I2C transmission using the wire.begin transmission function and pass the slave address as a parameter to this function. Next, we send a single character 1 to the slave device using the wire.write function and then complete the transmission by calling wire.endTransmission function. After sending the data, we print another message on the serial monitor indicating that we are now waiting to receive data from the slave. We then request 5 bytes of data from the slave at address 9 using the wire.requestFrom function. To read the incoming data, we declare an empty string variable named response. We then use a while loop that runs as long as there is data available in the receive buffer, which we check using wire.available function. Inside this while loop, we read the data 1 byte at a time using the wire.read function and store the returned byte in a char variable named character and then concatenate it with the string variable response. This process continues until all the requested bytes are read and concatenated with the response variable. In this way, we reconstruct the original message sent by the slave device. Finally, we print the complete received data on the serial monitor. Now, let's look at the code of the slave Arduino. It will receive data from the master and respond with a message. At the top of the code, we have included the wire library using the include statement and define the slave address, which is 9. Next, we define the number of bytes we will send back to the master, which in this case is 5. We then declare a string variable named answer and assign it the value hello. This is the message the slave will send back to the master whenever it receives a request. In the setup function, we initialize the Arduino as an I2C slave using the wire.begin function and assign it the previously defined address, which is 9. Next, we use the wire.onRequest function and pass the name of our function, requestEvent, as a parameter. This tells the Arduino that whenever the master requests data using wire.requestFrom, the requestEvent function will be called automatically. After that, we use the wire.onReceive function and pass the name of our function, receiveEvent, as a parameter. This tells the Arduino that whenever the master sends data to the slave using the wire.write function, the receiveEvent function will be triggered automatically. We then initialize serial communication at a baud rate of 9600 to display messages on the serial monitor. After the setup function, we define the two interrupt-driven functions, receiveEvent and requestEvent. As we know, whenever the slave receives data from the master, the receiveEvent function will be automatically called with a single parameter, indicating the number of bytes received. Therefore, we have declared an integer variable named numBytes to capture this value. Although we will not use this parameter inside the function, including it is mandatory for the function to work correctly. Inside the receiveEvent function, we use a while loop that runs as long as there is data available in the I2C receive buffer, which we check using the wire.available function. Inside this loop, we read the incoming data 1 byte at a time using the wire.read function and store it in a variable named character of char data type. Since the master sends only a single byte, no concatenation is required, and we simply print the received value on the serial monitor. Next, we look at the request event function. Here, we declare a byte array named response, whose length is equal to the number of characters in the answer string, which is 5. We then use a for loop that runs 5 times. Inside the loop, each character of the string hello is accessed using the char_at function, converted into a byte, and stored in the corresponding index of the response array. For example, when the loop runs for the first time, the value of the variable I is 0. The char_at function then returns the character at index 0 of the answer string, which is H. This character is converted into a byte, 72, which is the ASCII value of the capital letter H. This byte value is then stored at index 0 of the response array. The variable I is then incremented to 1, and the same process repeats. Each iteration converts the next character in the answer string into its corresponding ASCII byte and stores it in the next position of the array. This continues until all 5 characters are converted and stored in the response array. After preparing the byte array, we use the wire.write function to send the entire byte array at once to the master device. Since we are sending an array, we have 2 parameters. First, the name of the array, and the second, the size of the array. Finally, we print a message on the serial monitor indicating that the slave has successfully responded to a request from the master. The void loop function only contains a short delay to keep the program running smoothly. Since all I2C communication is handled automatically by the interrupt-driven onRequest and onReceive functions, no additional code is required inside the main loop. Now let's connect both Arduinos to the computer and open 2 separate windows of the Arduino IDE. We connect the master Arduino's COM port to one IDE window and the slave Arduino's COM port to the other. Next, we upload the respective code to each board, the master code to the master Arduino and the slave code to the slave Arduino. After a successful upload, we open the serial monitor in both IDE windows. At this point, you'll notice that the data is updating very quickly, making it difficult to clearly see what's happening. To slow things down, we increase the delay in the master sketch from 50 milliseconds to 10 seconds. And we also add the same delay just before requesting data from the slave. We then upload the updated code to the master Arduino and reopen both serial monitors. Now the process is much easier to follow. First, the master Arduino sends data to the slave, and a confirmation message is displayed on the master's serial monitor, indicating that it is sending data to the slave. The slave then receives this data, prints a confirmation message stating that the data has been received, and also displays the received value on its serial monitor. Next, the master requests data from the slave, and a message appears on the master's serial monitor, indicating that it is receiving data from the slave. The slave receives this request, sends its response back to the master, and prints a confirmation message stating that the data has been sent. Finally, the master receives the data from the slave and prints it on its serial monitor. This entire communication process then repeats continuously, demonstrating two-way I2C communication between the master and slave Arduinos. Now, as our second project, we will control the brightness of an LED on one Arduino using a potentiometer connected to another Arduino, entirely through the I2C communication protocol. To do this, we first connect a potentiometer to the master Arduino. The 2 outer legs of the potentiometer are connected to 5 volts and ground, while the middle pin, or wiper, is connected to analog pin A0. Next, on the slave Arduino, we connect an LED to digital pin 9 through a 220 ohms resistor, and the cathode of the LED is then connected to the GND pin of the Arduino. With the wiring complete, let's now take a look at the code. As before, we will be using 2 separate sketches, one for the master Arduino and one for the slave Arduino. Let's start with the master sketch. We begin by including the wire library and defining the slave address, which is 9. Next, we define the potentiometer pin connected to analog pin A0. In the setup function, we call the wire.begin function without any parameters. This tells the Arduino to operate as a master device on the I2C bus. Inside the loop function, we read the analog values from the potentiometer using the analog read function. This value ranges from 0 to 1023. However, since we can only transmit 1 byte at a time, meaning values in the range of 0 to 255, so we will have to use the map function to scale the potentiometer readings from 0 to 1023 down to 0 to 255. This mapped range is also ideal for PWM-based brightness control on the slave Arduino. Next, we start the I2C communication by calling the wire.begin transmission function and passing the slave address as a parameter. We then send the brightness value to the slave using the wire.write function and complete the transmission using the wire.end transmission function. Finally, we add a 50 milliseconds delay to keep the communication stable. And that's all for the master side. Now let's move on to the slave Arduino code. We once again include the wire library and set the slave address to 9, which must match the address used by the master. The LED is connected to digital pin 9, which supports PWM. This is important because we'll be using the analog write function to smoothly control the LED brightness. Next, we declare an integer variable named brightness to store the incoming value from the master. In the setup function, we configure the LED pin as an output and call wire.begin function with the slave address inside the parentheses. Since an address is provided, the Arduino automatically operates as an I2C slave. We then register an event handler using the wire.onReceive function, linking it to a function named receiveEvent. This tells the Arduino that whenever the master sends data, the receiveEvent function should be triggered automatically. Now let's look at the receiveEvent function. Inside this function, we read the incoming byte using the wire.read function and store the value in the brightness variable. In the loop function, we simply call the analog write function, passing in the LED pin and the brightness value to set the LED intensity accordingly. A short 10 milliseconds delay is added to keep the output stable. Now let's upload the master code to the master Arduino and the slave code to the slave Arduino. After a successful upload, rotating the potentiometer will smoothly control the LED brightness. Turning it clockwise increases the brightness, while turning it counterclockwise decreases it. So that's all for this video. We hope you found it helpful. Don't forget to check out our channel and visit our website for more tutorials like this, and we'll see you in the next one.